Okay. Okay, just for the recording's sake, we're talking about precession of the perihelion. In general, the Kepler problem deals with a potential of 1 over r potential, negative 1 over r potential. And in that case, it is periodic in the sense that when phi is equal to 2 pi, it is exactly at the same place as it was at phi equal to 0. That means it will keep repeating itself forever. But what if we make a small change to that, and then it's no more perturbable, it's no more a Kepler problem. It's slightly perturbed, and let's also say that delta U is very much small compared to U, right? The original potential that it was there, it is extremely small, and that's what it means to perturb the problem. Perturb means you change it a little bit so that you can use all your results that you had earlier, and you make the leading order change. What's the first correction that you can have? And usually this is a very popular technique in the sense most of the perturbations that we can think of are usually in the third digit. It's only 1% correction or so, but we are interested only in that very leading order contribution if we have mastered our original problem significantly. And that's what we want to investigate today. Okay, so let's go back and see in Kepler problem what are the conserved quantities. So this is energy was conserved, right? So that's half mu r dot square plus half mu r square phi dot r square, and that is minus g m1 m2 over r, right? That's your energy to begin with. We are going to keep ourselves in the time independent regime, and this change in potential will show up as plus delta U there. That's your new correction to what we were doing earlier. And this is the only change we will talk about. And LZ, the angular momentum is also conserved. We want to keep that as it is. So we would like to talk about perturbations that are still spherically symmetric. We don't want to talk about distributions which disturb our spherical symmetry. That means to say that you can, so the kind of perturbations that it will do is that, let's say the sun is not really spherical, it's elongated, right? Then what are the changes that will happen? So still it will be 1 over r, but the changes will be in the next order. Or actually, no, that's not correct. If it was, if sun was not spherical, then it will become angular dependence, right? So we are basically, yeah, how will you change this? Think of a force of this kind. So if I can write it here. So our potential energy is 1 over r, right? It could easily be e raised to minus beta r over r, right? That could be an exponentially decaying factor, and it might be very hard to, in the leading order, we may not be able to catch this. This is called a Yukawa potential. So the what we are going to do today will mostly be discussing effects of this kind, where the spherical symmetry is still kept and we don't change things.
Could you say what that was called again?
Call that again?
Could you say what it's called again?
Yukawa potential. So this is called Yukawa potential.
Okay.
This is like if you were to do radioactivity and nuclear forces, these explain at least, or these explain those forces pretty well. Or better, we have electromagnetism and gravity both deal with 1 over r potential, And what they have in common is that the associated field, which is the photon and the graviton. Is that a familiar idea?
Yeah.
Like charges interact through photons or light, and gravity interacts through what is called graviton. Both of them are massless. Like photon is massless, graviton is massless. Now, usually these interactions can happen through massive particles too. Like imagine a case where if photon had a mass, a very small mass, but it's not zero, but it has a mass. What would the effect be? And then the energy would change to this form, where beta here has the information of mass.
Okay.
You can think of 1 over mass.
Okay.
Okay, so that's so any massive potential will, or any massive particle in the interaction changes the potential energy to give an exponential form, and that's called the Yukawa potential.
Okay.
So yeah, so we have Jordan here now. Okay, so if we were to include that, what is the kind of perturbations you can have? Even if not, like for example, even if you're considering what is the effect of Jupiter, that's also okay in the sense that if you were to do perturbation in the leading order, you would say that you still have the spherical symmetry, everything in the leading order perturbation. So even in that case, it is allowed, but let us be strict here, and let's not worry about how that is coming about. Okay, so so that's a kind of perturbation we'll talk about, and an angular momentum is what, mu r square phi dot, right? Which immediately tells us that dt or d phi, right? D phi, this is d phi, is equal to Lz over mu r square times dt. Right, this is a so that what that means is that the angle evolution in the angle can be imagined to be a certain form of time, and you use this feature as proposed by Moses. You use this feature in your midterm problems, right? There, just this replacement leads you to be able to calculate time. Okay. Based on this, we did a few things. We did dr by dt. So I'm going to bring everything so that dr by dt is onto the left. And we showed that dt, right? So I'm going to do, yeah, let me do slowly. So, so it is, so dr by dt square will be equal to 2e over mu. Right. Bring this to the right. Bring this there. So that's so multiply by 2 and then divide by it. So this 2 g m1 m2 over mu 1 over r. I really have to enough space too much, plus 1 over r square, or minus now, minus, but I'll replace this phi with this quantity here. So you have, what is it, Lz square over mu square r raised to 4. So it is Lz square, but then, yeah, Lz square divided by, well, there's a mu in the numerator, 2 mu's in the denominator, so that's 2 mu. And then there is r square in the denominator, right? So that's this term here. that correct?
What did you do to the square of r dot in the first term?
I just kept it. Oh, I'm going to put a square root in here.
Oh,
Also.
okay.
So yeah. So if you allow me to do that at the later stage. So this
Sure.
is a square, that's correct, but I'm going to make a square root of the whole quantity, right? And did I get this correct? LZ square divided by, so there is a 2, right? Factor of 2 here, and there is a mu square that will cancel out. So that's correct, I guess, right? Yeah, so that's correct, right? So help, is that 2 there? Why am I struggling with the 2 there? Oh, because I'm multiplying by a 2 and then dividing by a mu also. So this is 2 is not there, and then mu square. Yeah, that's better. Because I'm overall multiplying by a 2 and dividing by a mu. So doing few things simultaneously, but we have gone through this before, so that's okay. So this is plus 2 times delta mu, whatever delta mu is, divided by mu. Right? And this whole thing. Okay, right, that's, so that should answer your question, Moses, right? Okay, so that's what it is. So I have used these 2 equations to write this. And from this point on, I can bring this square root in the denominator, dt, and I want to also replace this mu there. I will also do one more thing. I'll multiply by mu square everywhere. So a few things again. Just writing in a certain form. Okay. So dt is equal to, so let's say d phi. So d phi is equal to LZ square over mu r square, but then I introduce the mu inside. So I have LZ dr LZ over r square. That's coming from d phi and dt getting related, but mu I will push it inside, and that is a dr already. So let me say this is dr, and 1 over 2 mu e, right? Same relation, plus 2 mu g m1 m2 over r minus LZ square over r square plus multiplying by mu, so just 2 mu delta mu. Okay, did I do everything? Not yet, actually. Yeah, still processing. Okay, so in a certain form. Just manipulating. Idea is the same. We have energy conserved, angular momentum conserved, and based on the energy conservation, I can write this down. But we did this in a better way, and that's the following. Right? Yeah, and yeah. So how do I want to do this? Remember, we did 2 things. We had the idea that, let me write it on the other side so that I can write the next step there itself. Come on, move. Okay. We introduced some parameters last time based on, remember, we set the effective potential is of this form, and the minimum of this was called R naught, and the energy at the minimum was called U naught, or we called it U effective at R naught. Let's call that U naught, right? And these quantities we showed was R naught was equal to LZ square over mu times G M1 M2. Correct. I think that was our relation. Check on that. I can quickly check it. Yes, that's correct. And U naught was half of the potential energy at this. So this is G M1 M2 over at this point. So it's R naught. And it was exactly half of this. Right. So that's our a scale in the energy and scale for the distances. Note that this is negative, correct? That's an important point to keep in mind. Based on this, I can rewrite my quantities in there. Let me roughly do it here, and then I'll copy it there so that I can use the board space again. So whatever we had in the denominator was 2 mu E plus 2 mu G M1 M2 over, so that's, let me write this as 1 over R minus LZ square over 1 over R square and 2 mu delta mu. Right. Let me scale things around. So let me say this is R naught. I introduce an R naught here and an R naught there. Right. I introduce a R naught square there and an R naught square in the denominator here. and what else I want to do? Yeah. So that's pretty much for now, and that leads to 2 mu E. Like this is what was there in the inside of the square root, right? 2 mu G1 G2 2 mu G1, why is it coming in the opposite side? LZ square LZ square over, I think so, that's okay, right? So this is equal to plus, right? So I'll have LZ square, or I can replace this, right? Mu, what should I do? Mu LZ square over R naught square. So it is 2 times LZ square over R naught square, correct? And we have R naught over R. Yeah, good. So that's minus LZ square over R naught square over R square and plus 2 mu delta mu. Okay. Pull this out, LZ square over R naught. I think that's what I was trying to do all through. So we have 2 mu times E divided by LZ square over R naught square. And I have the rest of the things get simpler a little. So it's R naught over R minus R naught square over R square plus 2 mu R naught square over LZ square. These are all constants, notice just the delta U that's changing. What is this? LZ square over R naught is nothing but 2 mu times G1 M1 M2. And since that is a factor of half, you can see that this is U naught, right? If you were to replace one of the LZ square over R naught with mu G1 G2, whatever is remaining is just U naught, and which is what it should be. So we have LZ square over R naught square. I think finally I have this. So this is E. It's E minus E over U naught because of the negative sign in the U naught. And that's it, plus 2. We leave a little space there. 2 R naught over R. Two mu delta. Let me put a -1 here and a +1. And if you remember, this was nothing but your eccentricity, definition of eccentricity. This is eccentricity, E square. Maybe I should write that down here. E square was 1 minus E over U naught. Okay, just rearranging stuff. And this is 1 minus R naught squared. So if with that structure there, let me go back and process this a little. Okay, if you bear with me. Or else just, so there's an LZ square over R naught that's going to be brought out. LZ cancels out. So I have what you have is that LZ over R naught, right? So LZ cancels out, and what we have is R naught over R square dr, and 1 over E square minus. So there's a significantly simpler form here. Okay. And the extra term here is equal to some beta times delta mu, which is a dimensionless quantity. Is that clear, all the processing that I did?
I have one question.
Yes.
In the second line, second last line, you have LZ square over R naught square, but on the right, on the middle board.
Oh, on the right, sorry.
So in the second last question, you have LZ square over R naught square, but in the last equation, you have LZ square over R naught. How did it go from?
That's a typo. That's a typo.
Okay.
I forgot to write the square. Bad.
Okay.
Thank you. Thank you. Thank you. Okay.
I have another thing that I noticed. Maybe I just, so in the second line on that board, yeah, you have the 2 mu G M1 M2 over R naught times R naught over R. And if you multiply the by R naught, like going to the second line, I think it seems like
from here to here.
Yeah, it seems like you have just LZ squared over R naught.
No. Notice this is 2 mu G1 GM1 M2 is LZ over R naught, right?
Yes.
So LZ square over R naught comes from here, and there's already an R naught, so it's LZ square over R naught square.
Okay.
Correct. So mu G1, this denominator is LZ square over R naught, but there is an extra R naught because it's already sitting there.
Okay. Yeah.
So I think
that makes sense.
That's correct. Yeah. Okay.
I have another thing. In the last equation, well, it's not an equation, it's just a term. So in the last polynomial, whatever it is, are you missing? Yeah, I was going to say that.
Oh, you were just going to say that. Okay, good catch. Yeah. Okay, anything else? Jordan, how are you?
Alive.
Okay.
I'm good. I'm following.
Okay. Following. Okay. Okay. So just manipulating whatever we processed last time in one in an initial stage instead of later. Last time what we did was we just kept doing all this substitution one by one, and we kept doing it so that we get the answer. Because it was a solvable problem, it was okay to proceed. But here we have to be a little careful because it's not a solvable, or the integral will not be doable. So we have to keep it as much as in a nice form as possible. Okay. So in that sense, so this problem is doable if beta was equal to 0, right? And I should write what is beta here so that I can, because I'm going to be erasing things. So beta here is equal to, delta U is arbitrary, and it is 2 times mu R naught square over LZ square. Okay, that's what we have. Okay. And let's analyze that a minute. So, so let's set beta equal to 0. How about that? And get an identity here. So just to learn something, because when beta is equal to 0, it's an exactly solvable problem. That's a Kepler problem. And let's see how it works. So that's right on the left-hand side, but I'm going to rewrite that for you guys, right? So this is d phi is equal to LZ over R square without doing the transformation into R naught. So this is 2 mu E plus 2 mu G M1 M2 over R minus LZ square over R square. Okay. Now notice the following. There is an identity now. So we are going to, last time what we did was we actually did this integral in a blunt way. But one can use a trick here, that derivative of with respect to LZ, right? LZ is a parameter, that's a constant. Usually you wouldn't do that, but it's a parameter. Why not take a derivative of that, but not of this quantity here, but let's think of it, think of the following quantity, the square root that appears in the denominator. Let's take it to the numerator. So this is a trick we are going to use to solve a complicated problem. So what's the derivative of this? Remember, derivative of a square root of a quantity brings down the square root in the denominator, right? So this square root that is in the denominator can be generated by a derivative of the of a quantity inside the square root. When I take the derivative, there will be a factor of half coming in. Whole thing goes to the denominator, and then I have to take the derivative of this LZ square, which is minus 2 LZ over R square. So it is minus 2, 2 cancels out, so it's minus LZ over R square times 1 over 2 mu E plus 2 mu with me. So the idea is that why do it this way? Write this as a derivative And when beta is equal to 0, you have to do an integral with a square root in the numerator, which is usually significantly easier. Okay. If not in this case, especially with the perturbation scenario, since in this case we can do it in many ways, it is doable this way or the other way. But when the perturbation comes in, it is much easier when you have the square root and the numerator. Okay, so that's going to be the trick, that instead of having a 1 over the square root, I will lift it to the numerator by using this identity that this is a derivative of LZ. Okay. And then we will process the whole thing in there too. Okay. So I can proceed. Any questions as of now? Okay. So if beta is not equal to 0, so I can write d phi as equal to, it will be the same LZ over R square that will show up, but now it is minus derivative of d by LZ. Okay, and there is the whole dr times square root of 2 mu e plus minus LZ square over R square. And at this point, let me write it as just plus 2 mu delta mu. But I can always scale it out. We just now did that. So scale the whole thing out. And what we have here is whatever the factor that came out there. Right, what was it? LZ square over R naught is what we pulled out. So it is minus derivative of LZ over R naught times dr, and the same quantity in the square root, which is E square minus 1 minus R naught over R, the whole square. And what we had there was plus beta times delta mu. Earlier it was in the denominator, now it's in the numerator, except that now it is coming with a derivative of LZ outside. Same idea, otherwise everything goes through if it was the other way. Okay. Any questions at this stage?
Can you explain one more time the LZ over R naught before your DR?
I think because everything is not on the board, probably that's a problem. Notice there was this, once I had this expression here, to get it in this form, I had to pull out an LZ square over R naught square there.
Okay.
Right. So that is the,
I got
when
you.
I pull it out of that, there is an LZ over R naught that shows up there. Okay.
Okay.
Okay. And if you want, you can actually replace this R naught also with a, so also remember that R naught is is LZ square over mu G M1 M2, right?
You'll have to move
that's also
move the camera as well.
Oh, I moved my camera. Yeah. So remember, like instead of writing both LZ and R naught, it's good to remember that R naught is LZ square over that. So it is good to think of it as, so one of the LZ will cancel out. So maybe I'll prefer to write this as, so it was LZ over R naught. So it is mu G M1 M2 over LZ. So that's a derivative we have to take. Okay. If beta was equal to 0, this is how much will this be equal to? So now let's integrate this. Okay. So again, I keep flipping around from beta equal to 0 to beta not equal to 0. So let's set beta equal to 0 again for a minute. If I were to have beta equal to 0, and let me do the following integral. I go from the closest point in the ellipse, or let me begin from the farthest to the closest, right? So we are going, so this is my ellipse. Think of the Kepler problem first. Beta is equal to 0. I start from here and reach here, right? So this is R minimum or R max, right? R max to R minimum. Right? It will go from 0 to pi in that case. So let me do 2 times that. So 2 times that. So this is R max to R minimum. What will this be equal to? It should be 2 pi, right? If it was beta is equal to 0, we know that this will be equal to pi. So it is 2 times pi. So that's equal to, if beta is equal to 0, so that's minus d by d LZ mu G M1 M2 over LZ times, we do the integral, so it is 0 or R max to R minimum. What is R max and R minimum? Let me write that explicitly also. Remember, R max is R naught over 1 minus E, and R minimum is R naught over 1 plus E, right? So this is R max to R minimum, and this is dr E square minus 1 minus R naught over R whole square. And that's a identity if you want. This integral can be done. You would substitute 1 minus R naught over R is equal to E cosine phi, or pretty much the solution of the conic section is substituted in there. But now we want to set beta not equal to 0 and do the same problem. So let's say beta is not equal to 0. So this will be slightly different, and we want to make it a small change from what we have, what is going on. So we would say, let's say that I want the integral again. So it is E square minus 1 minus R naught over R plus beta times delta U. I would like this beta times delta U to be small compared to whatever is there in the front. So I would like this to be as close to that as possible. So this is E square minus 1 minus R naught over R the whole square, square root, and the change, right? That is your old solution. We know what that is. But now what is the change? The change is small, so expand this out. The square root when expanded is 1. So remember your square root expansion, 1 plus x is 1 plus half of x, right? Plus so on, and as a Taylor expansion. So it is 1 plus half of beta times delta u divided by whatever is in the as the first term without beta term inside the square root. So I'm going to squeeze that in here, e square minus 1 minus r naught over r whole square. That's the first term, and there are higher order terms which we are not going to keep. Is that clear? So that's the main part of the other than the calculation part. This is the main idea here, that we are going to take the square root and keep only the leading order. And the first term here is the old Kepler problem itself, and the second term is what is going to contribute. Okay. So what is that equal to? This is the same as e square minus 1 minus r naught over r the whole square. That's the first term. The second term is identical in the numerator and the denominator. Numerator has a square root, denominator does not have a square root. So this can be written as plus 1 by 2 times beta delta u over square root of e square minus 1 minus r naught over r the whole square. With me? So overall what we have done is, for beta not equal to 0, 2 times r minimum to r max d phi is equal to, like this should have been 2 pi if it was a Kepler problem, but it need not come back to the same point if it was perturbed a little, and that difference is equal to the first term, whatever comes out, we know the solution. This one, if I were to substitute into this, I know that that is 2 pi. Correct. So I will put that as 2 pi itself. That's my Kepler solution. And what is the change? The change is coming from this term, and now I had to put in all the contributions from the derivatives and the integral. So that's d by d Lz mu g m1 m2 over Lz, and we have an integral going from r max to r minimum, and here it is 1 by 2, so it is integral going from r maximum to r minimum, right? That is going from the maximum value to the minimum value, and dr beta delta u. Remember, delta u can have r dependence in it. I have not yet specified what delta u is, and we will specify that as an example. We'll specify it in a minute. E square minus 1 minus r naught over r. And the whole point is that that integral is doable using the same substitution that we have for the clinic section. So let's substitute, or let's take an example now, right? Let's specify your delta u also. So from this point on, let's do an example, right? So whatever this is different from 2 pi, that's your added or that decides how much it's going to precess off from.
So the left-hand side of the integral is also R max to R min, right? And not the other way around?
Oh, I no,
Limits.
yeah, R max to R min. Yeah, I switched. Yeah.
And where is the 2 pi coming from?
Oh, notice this is the first term, correct?
Hmm.
And the first term is nothing but beta equal to 0.
Okay.
Agreed?
Yeah.
And if beta is equal to 0, this answer we know is 2 pi because it's a periodic problem, the Kepler problem.
Mm-hmm.
Is that clear? I mean, I didn't do that particular scenario, but we have already done that in, let's say, in the last class.
Okay.
Is that clear? Did I answer your question?
Yeah, I think so.
Or else, how can I motivate it? If you look at this diagram, maybe, right? We are talking about integrating phi from here to there, right?
Oh, yeah. It's sweeping throughout the upper plane, right? Like, okay.
For plane, so that is pi,
2 pi.
correct?
Okay. Oh, pi.
And then 2 times
Yeah.
that will be 2 pi, right? So
Okay.
Kepler problem, that is straightforward, but in the new problem, we don't know whether, it might only come here, right? Or it might overshoot, it might also go there. We don't know whether it's going to be plus or minus, that's decided by delta mu.
Okay, I get it. Yeah.
So that's that 2 pi. And so that's the delta phi will be the precision part, how much ever that is. Okay. Okay. So at this point, let's do an example. Let's do a very trivial example where delta u is equal to something divided by r square. Let's say. Okay. So this is r square. What should I put in the numerator? I've not used alpha. Well, let's not use alpha. Alpha, beta, gamma, kappa, right? Kappa maybe. Okay, kappa over r squared. Beta is already there. It has all those coefficients in it. Okay, with me? Okay, so what we have then is pretty much an integral involving 1 over r square, and there is r squares in this. So let's do that integral, and the whole manipulation was so that that integral is doable. Okay, so let me remove this. I think this I was just. Okay, so if I were to introduce delta phi as 2 times r max to r minimum d phi minus 2 pi, let's say. Right. So delta phi, which is a precision angle, is minus d by d lz mu g m1 m2 over lz times an integral of r max to r minimum dr beta and kappa over r square. So this is kappa over r square, and I have 1 over e square better. So let's substitute here 1 minus r naught over r, like there is this cosine 1 minus cosine square structure there, right? So that's equal to e cosine phi. That's pretty much your conic Kepler problem solution, right? R naught over r 1 minus e cosine phi, that's your solution to the Kepler problem, but we are substituting it in the non-perturbed Kepler problem, right? So this leads to minus, if I were to integrate this, so this will become r naught dr over r square is equal to to minus e sine phi d phi. Right, notice dr over r square coming up, dr over r square will get replaced with e sine phi. So that's the key. And if there were higher terms, it will be in 1 over r form. It will always be in the numerator. All the trigonometric structures will be in the numerator. So it's not that I'm picking a very special quantity in there. So delta phi is equal to minus d by d of z mu g m1 m2 over lz. And I should also worry about the limits when r max is substituted. So when r max is when r is equal to r naught over 1 minus e becomes plus, so that's phi equal to 0, right? So e cancels out, so that's phi equal to 0. And when r it is the other way, so it's a cosine phi is minus 1, so that's pi. Right, so what we are doing is, let me give an example. So 1 minus, so this is r naught over r naught, and this is 1 minus e, that's equal to e cosine phi, right? That's what happens when it is a maximum value. That cancels out, so this is e is equal to e cosine phi. That means phi is equal to 0, right? That's how I got the same thing with pi. dr over r square is e over r naught, so it's a minus e over r naught sine phi d phi. And here in the denominator, I've substituted 1 minus cosine square comes in. There is already an e, so there is a e cosine phi. Also, no, sine phi, right? Because if I substitute it, it's sine phi. Only for this 1 over r square potential, this becomes straightforward. Sine phi cancels out, and I get a simple integral of d phi. If it was any other potential, there will be extra trigonometric terms in the numerator, but all doable. Like it will be all in the numerator because 1 minus cosine phi will be in the numerator. So there will be cosine phi terms and so on coming up, but they will all be doable. Only in this special case, this is slightly simpler. So e cancels out. So this is plus plus. So this is what is this equal to? Help, minus comes out. So this is d by d lz over mu g m1 m2 over lz. E cancels out, sine phi cancels out, and the integral is just pi, right? So pi over r naught. Pi over r naught. What is r naught now? Remember my r naught. Help. R naught was what? R naught was LZ square over mu G1 G2. So there is another LZ square in here, and there is a mu G1 G2 in the denominator. So this is equal to pi times d by d LZ. Again, yeah, I think that's correct. So this is mu G M1 M2 square now over LZ cube. From this point on, it's just a matter of finishing up. We know how to take the derivative of LZ square. Did I miss anything here?
I don't think so.
No, kappa, right? Beta and kappa. Yeah, I missed beta and kappa, right?
Oh yeah.
Right.
Yep.
Yeah.
Yep.
Right. So there was this beta and kappa. I sort of dropped somewhere, right? So dr over r square, I took care of it as e over r naught, but then I forgot the beta and kappa. So I'll put that in here, beta and kappa. Okay. Okay, that's better. So, and there is a beta and a kappa. Like I'll put that here in front. That's equal to beta and kappa. Okay, great. Oh, I should carry it out, right? So there's beta and kappa. This derivative is easy on the board. Yeah. What is this? Minus 3 over LZ raised to 4, right? Straightforward. So it is minus 3 pi times beta kappa, and I have mu G M1 M2. This becomes LZ raised to 4, so I can write that as LZ square and square, correct? Because it's LZ raised to 4, it can write it as LZ square. But that is nothing but 1 over R naught, right? So in that way, this is equal to minus 3 pi times beta kappa over R naught square, if you want. Okay. And I haven't specified exactly what kappa is, but some dimensionless quantity which can be calculated for a specific problem, and presumably this will be small. Like it shouldn't come out 3 pi. This should not come out to be 1 at all. This will be very small because only then the perturbation problem is satisfied. Otherwise, we cannot neglect the higher order terms. This will be preferably very much less than less than 0.1 or something. And then this is a small perturbation from there. So the Kepler problem will not look like this. So this will go like this. If I can draw this. Have you guys seen this?
Mm-hmm.
Like, you get the picture, right? And that's a way to calculate that. This also, I usually go slow on this so that you clarify what perturbation is. Make us solve a problem, or first learn how to solve one problem, then make small changes to that, and you can learn a lot out of it. Right? That's how most of the time, that is how you do it in real life. You first learn how to solve one problem and then build on that by making small changes to that. and that's perturbation. And I finished it right on time. 2 minutes to go, not bad. Okay, so yeah, we did perihelion of precession of the perihelion. And this perihelion is the tip of that ellipse is called the perihelion. So that's moving around. So that's called precession of the perihelion. So that's a terminology out there. Okay, good. Questions, comments?
I have one quick question about that. The later picture. I'm
This
just
picture?
wondering if an object will go to its initial position when there's a perturbation.
Okay, so there is a theorem that only for 1 over r square potential, or the 1 over r Kepler problem, and there is one more, it is harmonic oscillator potential, r square. That's the only two situations when it will come back to that same point in one period. It might come back later on after many rotations, it can come back to the same point. Was that your question? Maybe that was your question.
Yes.
Oh, your question is after about 10 revolutions, can it come back to your original point or not?
Maybe infinite. Doesn't matter if it is 10 or 20. Does it ever?
Oh yeah, 10 or 20, some finite number. It shouldn't be infinite because then you lose everything, right? So in a finite number of rotations, can it come back to or not? Yes, possible, but I think that will depend on, that will depend on this quantity being a rational number, not an irrational number. Right? If it's a rational number, then it can come back like after specific number of rotations, it can come back. So very special choice. Yes, it can come back. Did I make sense? Why rational number?
Yes. Irrational number.
Like then it's an integer fraction that shows up.
Yes. Thank you.
Yeah, good question. Yeah.
So is this problem easier to solve like relativistically? Can you do that?
Oh, I think what you're asking is that, okay, so here is the story. So you learned, or Kepler gave his laws and Newton gave his equations that could explain those laws. And this was in 17th century, 1650s. And we got, we means the community got very efficient at doing these problems. And now what you practically do is you first take care of the planets. First you take care of Jupiter, right? That's the most massive object in there. And then you start taking care of all the possible planets and look for all the perturbations. And then you make the measurement of the perihelion also. Measurement of perihelion is very easy. And it couldn't explain the precision of the perihelion of Mercury. Okay. So accommodate for every object that is around Mercury, Sun, Jupiter, all the massive objects, and you couldn't explain the fact that Mercury's perihelion is precessing at some rate. It could accommodate for maybe about 20%, 30%, but it couldn't accommodate for the whole precession. Okay. And that led to the idea that maybe we are missing a planet. So imagine you are so confident about this result that it has to do this. Right? Newton gave his equation. Every other planet is doing correct, except Mercury. You are not able to explain the whole thing. And remember, Mercury's eccentricity is very large. These calculations depend on the eccentricity a lot. So other planets also do it, but then the error is so much you don't really get off the result too much. But Mercury, you're not able to explain it. So you're so confident about Newton's law that they went ahead and predicted or postulated that there has to be a planet which we are not seeing. So where can a planet hide? They said that it must be so close to sun that we are not able to see it. Like it is so bright, we never see it, but it must be there. And that was a prediction made, I think, in before relativity, about 1850s, 1860s. So very dramatic stories, sort of. I think that's what is called the Vulcan, maybe, like the Star Trek planet. I think maybe that's named after that. I'm not sure about that. But anyway, so now all this comes, but what relativity could do is, relativity could explain this precession of Mercury without accommodating for an extra planet. Relativity has, so a Kepler problem itself is not periodic in relativity. In relativity, even the Kepler problem, which doesn't show precession here, will have a precession of its perihelion. Does that help?
Yes.
The answer is that Kepler problem is not periodic in a relativistic case in the exact sense, because relativistic equations are more correct than Newtonian problem. It's wrong to say that it's actually periodic. So what we are doing is wrong. So that's how we put it. So whatever I've done today is not correct in the sense that right at beta equal to 0 itself, it should be showing a precession of the perihelion, which relativity can capture, not Newtonian physics.
Okay.
So that's the history of, that's why it's popular. So this was one of the predictions made by, or this was one of the right-away predictions, right, that it could explain. But that was not a very significant. Now one could ask, in 1916, when this was first time done, precession of perihelion was not used as a verification for general relativity, Einstein's equations, because these are really tiny. The precession of perihelion is such a tiny observation that you could always claim that, oh, experiments are not perfect, astronomy observations are not good. So you cannot rest a theory on an experimental observation which is too tiny. So they had to wait for the bending of light during an eclipse, which happened in 1917, I think, 1917 or 1918. So it was so the real acceptance of Einstein's equations happened only about 2-3 years later, even though this came up in 1916 itself in the first couple of papers that he wrote. So it had to, real popularity or acceptance among the community came only in 1917, 1918. I think it was 1918 maybe, whenever the big eclipse happened, where Eddington went and observed it, and he wrote a paper, and Eddington was a very reputed scientist, so his observations meant a lot. So that's how the story is. Yeah.
So if you were to solve this relativistically, would you just treat it as like a particle? You just treated it.
Yes, it will still be a particle, but what will change is the metric. Right now, in relativity, we don't have this potential coming out like this. Like, can you see that? Okay. So in relativity, we don't work with potentials at all. Instead, we say that there is a metric. Let's wait. How about this? Okay, 2 weeks. We are going to talk about relativity for 2 weeks, but we won't be talking about general relativity, right? So we won't be calculating the perihelion from using relativity. But what happens there is that the metric, but I don't think I have conveyed you enough. How can I explain this?
That's the Schwarzschild metric.
That's correct. That's exactly correct.
I think
So,
I remember
yeah,
looking at some of that stuff.
that's correct. So we say that there is sun there, and there is another particle, which is the Earth there. But there we don't have any potential, doesn't come out as we write it here. It shows up in the metric itself. So metric is interpreted as a potential, or in some form interpreted as a potential. or you can say the energy is constructed out of the metric. Okay, so that requires a few more statements from me. Maybe I can, the end last lecture, I can maybe tell something about that last lecture of our course, maybe.
Okay.
I guess I don't totally understand what's meant by metric.
Tell that again?
I don't understand what is meant by metric in this
Yeah,
case.
yeah. So how about this? What I can do is, okay, in relativity, typically what I do is, okay, so how is it going to go from the next 2 weeks, right? So I'll start with the standard relativity that you know, special relativity. And typically we just learn length contraction or time dilation that you must have seen in some form or the other in at some popular level or some introductory physics courses. But the important problem is the uniform acceleration problem. If a particle is uniformly accelerating in Newtonian physics, it takes the trajectory of a parabola, right? But if it takes a trajectory of a parabola, it will go faster than speed of light pretty immediately, right? Very quickly it will go, if it is accelerating, it will keep picking on speed. Eventually it will go faster than light, which is not obviously correct if we are saying that in relativity things cannot go faster than light. So there is a correction to that, or in the more correct sense, it's a hyperbola. So the particle, a uniformly accelerating particle, takes the form of a shape of a hyperbola. And this hyperbola problem, now I can flip the whole problem and say that, what if I want to talk about, what if I want to generate uniform gravity in the way general relativity would have captured it? Like I just now told that this is not the way I would do it. I would introduce a metric, correct? And in the metric, this should be inbuilt in there. So as Jordan said, Schwarzschild metric has this inbuilt in it. So we will construct some coordinates or a metric which has uniform gravity inbuilt in it, which is the most elementary general relativity you can do. And that is called, what is that? That's called Rendler coordinates. That's the simplest problem in general relativity. It is still flat space. We are not curving the space. It's still flat space, but you can have uniform gravity in there. And since we will be working with uniform acceleration, it might be just one step ahead, and I might be able to cover it in the last lecture. Might be able to. It will be ambitious, but let's try that. Okay. So the point is, a metric is a way you would, yeah, well, I'll introduce it in the last class.
Sure, sounds good.
I have another question about it now, though.
Yeah.
What assumptions do you have to make about the metric itself? Is it like spherical or?
Mostly not. Oh yeah, assumptions in that sense you're saying. Okay, so in so for example, Schwarzschild metric, the only assumption you make is that it is spherical and there is a mass at the origin. So sun is massive, there is some mass m which is at the origin, and then there is a test particle which is going around. It is test particle, not an actual mass. And you say that this is spherically symmetric, and that leads to Schwarzschild metric. That's a solution.
Okay.
Does that help?
Yep.
Yeah.
Yep.
Yeah, since I'm not writing down the equation of Einstein, it is hard to even tell the first couple of lines, but I might be able to motivate that in the next few lectures, because we will have metric floating around a little bit. I usually hide it, when I'm teaching relativity, because it's easier not to mention metric at all and proceed. But maybe here and there I can mention it, and then you will get a feel for what a metric is. And then maybe I can tell something at the end of the lectures. Okay. Like special relativity can be thought of in terms of metric, or it is in terms of metric. It's a flat metric. It's called the flat space.
Oh,
and
so
we have
it has to be, then the system has to be spherically symmetric and flat.
Here it is, no, not in Schwarzschild. Schwarzschild is not flat.
Oh, okay. Okay.
Like spherical symmetry, it's not flat, yeah. Schwarzschild is not flat space. That's a, Schwarzschild metric is the classic case where you take an elastic surface and you put a mass m, it dips down. Have you seen that? I mean, everyone, right? So that's Schwarzschild metric, where the mass
Curves
changes
the space.
Yes, that's a standard classic interpretation there.
Okay.
Okay, so there are other metrics, for example, the Friedman metric that is useful for cosmology. That's when the whole thing is evolving in time. There is no mass, but there was a bang in the beginning and it's exploding metric kind of. It's a time evolving metric. But again, yeah, so that's all. That'll be nice. I always think that, okay, in the end, we should accommodate some form of general relativity. But this time we couldn't even cover the necessary things. Yeah. But that was because we lost a week in the, because of what's happening, and we lost a week here and there, probably more than, mostly probably because I keep wasting time in the beginning of the lectures, so my fault. That's one thing. How was the pace of the lecture today? Was it acceptable? Was it too quick?
No, it was fine.
Fine, okay.
It was a little fast
This
for
is
me.
how
I'm gonna watch it again.
Yes, Moses?
I just said it was a little fast for me. I'm gonna watch it again to make sure I catch everything.
Like in the 5 years back when I started teaching, I used to go faster than this. But then I realized that it's much more effective when I go slower. So I kind of cut on some topics and started going slower.
Mm-hmm.
I think okay. Going fast is okay because we can rewatch it. So it's
yeah,
okay.
Especially in these recorded videos, probably it's okay, I guess. Yeah. And it leads to less discussions also. That's the price you pay, but maybe it's okay. Yeah, let's see. So next few lectures I might. Yeah.
I would say this. One thing I've noticed about the online stuff, as opposed to being in person, is that, and I mentioned this a little bit to Moses and talked about it a little bit in our quantum mechanics class, but if there's not like one thing you miss with these types of lectures is that just being on campus allows us to communicate with each other, which
yes,
the communication makes it a little bit more difficult to, like, for instance, just doing the homework itself, just having one little question you can ask somebody that gets an immediate response from them when you see them is beneficial in some sense. True. And also having, I think for like online stuff like this, it would be beneficial to just have a text that you referred to specifically, because a lot of those questions might be answered in that text. Whereas if you don't have a specific text, you're left searching through what you have or what you chose at the beginning of the semester. Like, okay, I chose a few books to buy. I don't really have access to a library. The school's
and no one has access to the library now, right?
Yeah. So
except the online stuff. No, you're correct. I agree completely to the first part. The second part, I cannot do much. Yeah, the textbook is a hindrance, and I'm sort of for not using a textbook, because then you explore a little. I feel that's education. And the first part, mostly, I'm a big like I'm really big into communication. Like, unless you talk, and that whole education is not just doing homeworks and getting grades, but that learning has to come from talking and just listening to people, what's going around you, and that cannot be replaced. I think online cannot do that. In fact, that kills the whole purpose, I feel.
Mm-hmm.
So I'm a big advocate of the standard traditional education, or traditional university environment.
Yeah. But I was saying, you know, I think the reason a textbook would be good for online is just because there's no, you can't replace, like, we can't just make meetings constantly through Zoom and hope to get the same understanding while, you know, holding a piece of paper up to the camera, or it's just not the same. It makes it difficult to follow. And then it feels like when you're doing the homework, there's even less time. Things seem to fly much quicker, because normally that time you would use, like, just asking someone a question and getting an answer, you're investigating through an infinite number of possibilities online, and, you know, you try to review the videos or whatever, but it's usually, it feels like there's a lot less time while doing
Agreed.
assignments,
Yeah.
even though there's
So that's
probably more time. So
No, I agree.
for instance, like Moses and I had, whenever I would have help desk, you know, there was always Avinash or Angela or somebody would be walking by, and they would see you working, and they would ask a question, or you'd be sitting there and you'd see them walk by and you'd ask a question, and then you'd have a conversation for 30 minutes about, okay, how do we process through this next step? That is non-existent, and you're left to your own devices a little bit, which I'm sure it's okay for some people, but for me, I need to see how people think, you know? So
No,
it's,
I feel you're very right to the point, and I would say you should talk about this. All of you guys should talk about this, because I feel there is a push towards online education. It is cheaper. There are lots of reasons why there are people are talking about it. Like, there is a very slow push on it. It's not that it's going to happen in few months or anything. It's a very slowly things are getting pushed towards online, and these things has to be talked to the policymakers. I mean, I hope they realize what they're advocating for, and whatever you said exactly, like when you're sitting and doing your homework and someone else comes and asks a question, and they have independently worked on it. Like, so let's say Moses has worked on a homework problem, Angela, Avinash, and you guys are all four of you spend time thinking, and suddenly while walking you see each other and you mention something that's irreplaceable.
Yep, I agree.
So
I think the
but yeah,
online,
I can only do, yeah, go
I
ahead.
think online class is like a vending machine, you know? It's like, what are you learning today? You put in your quarter and you get your, you know, Cheerios out of the vending machine, and those Cheerios
Very
are,
regimented. If you say that, okay, this is what you'll study, this is what we'll ask in the exam, this is what it is, if it is all very programmed, then online is good. But education is not that. The true education, I mean, I'm not talking about grades and having a strict curriculum and finishing the curriculum.
not to mention just being, if it might be a little better if you could right now go to a public library and sit in a quiet room, but when you come home and you just have the distractions of your home, it can be a little more difficult, I think, to, you know, you look out the front window, the front grass is growing, and you got to go out there and mow it. If I'm sitting in a library, I don't see the things I need to, you know, that need to be done. So, so I think being at school
yeah.
is nice. So
Yeah,
hopefully
no,
things get
I
better soon.
agree. Yeah. Yeah, but you guys should talk about this more in the community. Like these things has to be brought out.
It's difficult to. I mean, who do you even talk to in this at this time?
No, just talk to each other. I think it will spread. I hope it spreads. Yeah.
Yeah.
Like
But
just now, I
what would
think
you
3
do
days
in a
back, I saw an article. 3 days back, I saw an article in, I think it was SIU Today, right? Where everyone was for, oh, we are doing so good with online education. We are perfect. This is, I would like to use this in the future also during my normal classes. That seems to convey the point that, convey the opposite, that, okay, this is all going great. But no, I think one has to point out that no, it is not going great.
So to play devil's advocate just a little bit, there are, I think, some benefits to online courses, but not in areas like physics or probably mathematics or some advanced sciences where it requires you to see other people think. I think something like, history, which has a subjective but correct answer, who won World War II? Something along those lines. You can,
No, but then probably that's not what education in history about. It's
yeah.
like saying physics also has derivative, like let us say Newton's law for an inclined plane. That's a very well-defined problem. There are hundreds of videos of it out there. So you don't need to go to school for that. But I'm saying education is more than just the inclined plane problem.
I agree.
Similarly, history
I was just trying
probably
to
is
think of
more
a way
than when
to,
was the World War,
yeah,
right? So,
yeah.
like history, especially because it is so much on discussions and
Yeah, maybe history
yeah,
was a bad example, but I was just trying to play
yeah,
devil's advocate, thinking why they might think that. But maybe it's just purely a money thing. I'm not sure.
yeah, at least like that whole process is there, which I feel even on a normal scenario, that interaction is important.
Mm-hmm. I agree.
Even though I'm not a very social person, but still I would say that interaction is important. Whatever to a small extent, even reading the literature is an interaction. Someone writes and you debate it in the next paper, that's an interaction.
Yeah.
Let's say Moses says that negative mass is allowed. And after 3 months, Jordan writes another paper, now negative mass is not allowed. That's an interaction. That's how science works, right? One paper comes and the next paper builds on to that.
As long as you have a subscription to read the paper.
Isn't it true that these days, because of the advantages of online, right? They made the papers free. Some AIP, all papers are available as of today, apparently. But these days, especially, it's easier to access. Yeah. So, anyway, yeah, those are challenges. Yeah, those are also one should make free. I agree. But yeah, Anshula and Avinash, you guys are quiet.
Pretty silent spectators.
Pretty what?
Silent spectators.
Oh, silent spectators. Yeah, good. Okay.
Yeah, I just enjoy being around the people in the department, and I think it's helpful for learning to just be in that type of environment. And it's easy to see when you're slacking because there's always somebody that's not slacking. So when you're slacking at home, you can, you don't see anybody else, so you can justify, I'll put this off till later.
True.
When you're at school and somebody comes up to you and they said, hey, I finished assignment 8. Have you finished assignment 8 yet? And you're like, or no, better get to that.
Peer pressure, huh?
Yeah.
I
Just
don't know.
motivation.
there's something about home that makes me, I don't know, that makes me dumb. Whenever I stay in home for more than a day, my brain stops working.
Yeah.
Interesting.
I will say that I spent a long time on things that I don't think should be taking that long. I seem to be a lot
You're less efficient at home, you're
Yeah.
saying.
Mhm.
Yes.
Yeah. I think some people might be efficient at home, but it's not easy to be.
Not me.
I think yeah, I mean me either. But you know, I think a lot of people, if you go to work and you come home and you get home, you think about it as like a time to just relax a little bit, you know, focus on recovery. So it's a very mixed state currently. Is this a place where I'm supposed to relax, or is this a place where I'm supposed to get all of those things done that need to be done? So it's difficult, but
There's got to be some kind of distinction that you create, whether it's like you have your own space for working or a certain time or certain conditions or something, but without that, yeah, it's like so fluid and like it's, yeah, like I'm in my bedroom right now. I'm attending class. I'm literally sitting in my bed. And I would not say that that's ideal.
yeah.
But there's plenty of room to play around with other, you know, other ways of doing it, other ways of kind of creating that, you know, distinct mode of being at work or being at school.
Yeah, no, understandable. Yeah. I often work from home also, so it probably didn't affect me too much on that.
Mm-hmm.
But I do know what you guys are saying, because sometimes when I go home when I visit my parents, then it's harder for me to work. And I always associate it with there are so many thought processes that's happening. Like then I'm attending to problems that's many ways different.
Other things are drawing or vying for your attention.
Mm-hmm. Yeah, so that's how I could at least explain my not being efficient there.
The other thing, one of the other main things I think is really hard about this is that if let's say I have a question for you and it's on some homework that I've done. In order for you to see that, I've got to convert my homework to a PDF and send it to you. And then you have to write on the PDF itself where, you know, circle something. Maybe you should take a look at this. And without just blatantly giving me the answer, this conversation between PDFs is going to be like 4 or 5 PDFs long, sent back and forth where we're editing a PDF in order to get me to think the way that I need to think about a certain aspect of a problem, or it's just, it's cumbersome. It's
so in research collaborations, like how we work is like you guys might have something like this. Can you see this? So this is pretty much a big mouse, right? There's a USB connection, right?
Yeah.
And then you can write on this. So whatever the Zoom has a whiteboard, right? Or whiteboard, what is it called? Sharing screen, if you have used Zoom. Probably other teachers are writing on the Zoom whiteboard, correct?
All I know is Dr. Mosenberg is doing that.
Yeah, Dr. Mazumdar uses it. And how do others do it? Like, how's your other classes working?
Me?
Yeah.
There's this a PDE teacher who just sends out hand notes.
I see.
And complex analysis teacher, he gives out hand notes and he records the video for both graduate and undergraduate classes. So there's a lot of proofs. So he says if you don't like, you can skip it.
But how does he work it out, or
Yes,
does he just
he works out on the board. He just takes a video
Oh,
of him working
so
on the
there's a
board,
video
and
recording, so something like what I am doing, yeah. But what I was like, most of the, at least in physics, I think it is coming, or at least when I collaborate with others, like what Jordan is saying is, how do you communicate between Cape and Carbondale without physically being in the other place? So I will have this, right? And I can write on a screen, and you don't even need Zoom. So there are lots of whiteboards on the computer, and you can write there, and the other person can see it.
But the other
So
person
it's
needs to have it as well in order to communicate
be
back.
able to write it back. That's correct. So
So-
that's what I was trying to say, that yeah, if you have it, or most of the people I've seen, they have iPads and all. So that's how they manage.
This again comes back to a point of being able to afford it, right? I mean, not every
Agreed.
student can do
Yeah.
that.
True. Agreed. So that's the challenge, and especially because you guys did not need it as of now, and suddenly we are demanding it. So that's the difference. It's not very expensive, especially if I think vacuum is probably $50, $60.
Yeah, well,
but there must be $20 stuff available.
I got one through Bob, because Bob ordered a bunch of them, and if any graduate student wants one,
Got it. Yeah.
you can just get one from him. So
Yeah, because whenever I do my help desk hours, it's always like chicken scratch on the board when I'm helping someone. So I'm using my mouse, and then the whiteboard itself tries to autocorrect my shapes, and sometimes like a circle turns into a straight line. It's like, I'm sorry, just give me a second. Let me try to write this zero here. It takes you 5 minutes to write a zero.
No. I agree. No, I'm not trying to say that this can be solved, but yeah, agreed. I'm not trying to say that it has lots of limitations. Yeah. Lots and lots of limitations. We are now nowhere close to having a proper communication.
And then everybody has the professor
It's
that's
online.
a poor communicator, that you try to communicate with them, you send them an email, and you don't hear back for a week, which is like 5 days after your assignment is due, or it's a poor atmosphere. And I'm sure it's exacerbated by the fact that everything was in person, and then on the flip of a coin, within 1 week, it was like, hey, we got to go to online for at least the rest of the semester. So nobody was prepared for online courses, and man, I would say, like, I feel like I'm learning a lot still in this class, but it's way more of a headache. It's more of a, like when we were in class, you could ask us questions that we would go home and think about, and it was enjoyable. Like, I was enjoying the course. But I would say now it's more of just like a task or a duty. I'm enjoying physics less like this than I was previously, which I think is the last thing you want to do, is demotivate someone.
Yeah.
Which I think it's happened to some extent with me.
That's bad. That's okay.
And it has nothing to do with you, obviously. I think it's just the circumstances.
Yeah, but at least in this class, I dealt with some circumstances, right? I had a lot of choices. Like, one of the choices, for example, from whatever you're saying, is that I could have decided that we don't have to cover a lot of stuff, slow down, make the homework simpler, and keep enjoying the course. That was a choice I had. Even now I have it, right, for the next 2 weeks. But for some reason, I'm thinking that, okay, let me keep the curriculum, and let me go faster, and at least they will be exposed to the concept, if not appreciate the concept.
I think there's value to that too as well. But all I'm saying is that in general, in the online courses, I'm enjoying them significantly less. I'm enjoying the topic of physics a lot less because it's just, it feels like a big cram. It's like any extra time you have, you're, spent trying to figure out what somebody's communicating in a less convenient way. So.
Yeah, to that end, I should say, I mean, that was the purpose of that email, I guess I wrote a few days back. I think 2 days back, I wrote an email to you guys. I took away the deadlines for the homeworks. And I should say that if possible, try to appreciate the subject over finishing the everything. This is a special semester and a special time in various ways, and the grading also will be very different. There will be a lot of leniency, especially in the graduate level courses. So there will be lots of leniency. So don't be stressed out about all this. So that's my point.
No.
Okay. So
I'm not,
I had a choice of doing, like there are lots of options in front of me and I'm picking to go this way. Yeah, you were saying something, Jordan.
I was just saying, yeah, one thing I've noticed just even with grading the students that I have to grade for, it's like you can visibly see the deterioration of their the quality of their work. It's just,
of course, and
every
a
week,
significant deterioration.
yeah,
It's not just small.
every week there's less people that turn in their lab. There's and the lab is being done for them by somebody else via video with
But
results.
still it doesn't reach you, huh?
No,
Wow.
in lots of cases, I'm getting emails saying, hey, can you reopen, or I had this or that going on, my grandma's got corona, or it's like, it's, circumstances are different, but, and then in some cases you can see the students who just want to be excessively lazy, and they were lazy before this, but now they're progressively even more lazy. It's
So is
it's
there
not good.
have you guys among the teaching assistants decided how you would take care of the circumstances for the grading? Like, are you guys,
I
for
think
example,
when
now
we,
that the lab is being recorded and being given to them, let's say 3 of them do not submit the labs or 3 labs are missing. How are you going to be lenient about this, or how does it work? Like, do you have any, have you been advised?
we
Or
had
have you guys
one
talked about?
for the 253 A and B labs, we had one, and 55 obviously, but we had one real conversation, I suppose, at the beginning. And, I brought up the question. I said, most of my students do lose lots of points on their quizzes. And that's kind of the balancing factor, and tells me like which student is, understanding the material better than another student. But now the quizzes are online. So my fear was like, how do you, for the lazy student is going to achieve the same grade as the non-lazy student if they turn everything in, because the labs are, if you write the steps that the lab technician took to perform the lab, the procedure, and then you write the introduction, which is just like regurgitating what they've already said in the lab itself. Sorry, my dog was about to bark. And then write the analysis that they're essentially saying to you verbatim, and then explain the results. You can't really miss points on the lab. It's very difficult to grade them on that. And then now the quizzes where they typically lost their points, where you would like a student may go from an A to a B or a B to a C because they don't really understand the content. all students are suddenly getting a 30 out of 30, you know, on every quiz. Either they collaborate or, you know, it's easy to find the solutions to some simple solenoid problem online. It's so they just said we're just going to be lenient. It's just how this semester is going to be. And I don't know how to, as a TA, I don't really know how to handle that. And then as a student, I don't really know how to handle it either. So it's just a big mess.
Yeah, true. I mean, because we don't have anything to look towards, right? This is the first time.
Mm-hmm. Yeah, it's a good practice, I think, you know. I think when COVID,
well, you know, this might be an every year event that we will have a virus vacation.
Yeah, oh gosh.
It might come back in fall.
COVID 2021.
Yeah. 21, yeah.
Well, I think they said that some of the labs are in like phase 3 testing, which means believe that's the phase before typically a you know, a shot might become available, a vaccine. So I think they're getting closer to having some sort of vaccine for COVID.
Hey, I heard that the virus has already mutated and there's a third strain walking around.
Probably so.
Where did you hear that?
In the news. There are 3 strains now. Yeah.
Okay.
So if they found a vaccine for the second strain, it's not going to work for the third strain.
Yeah.
So where does that leave us?
I guess right where we're at in our homes, learning precessions of perihelions on boards.
It's been wonderful talking to you guys, but I gotta run.
Okay, yeah, I think I have a class also in an hour. I think one of you guys is there. Yeah, okay, I should work on it. Yeah, good. Yeah, but this should be, talk among people. That this cannot go on. It's better to face the virus than staying in.
Yeah, I think one thing that they could do maybe in the future is have like a platform where it's like an open classroom, kind of like a virtual classroom that people can just join that are in similar classes and just discuss, you know, just having a place where it doesn't have to be set up student to student, where it's already like, hey, here's a virtual classroom where you can just join and have a discussion about whatever class you're in.
That is possible here, right? I mean, if you guys really want, that can be done. Like you can open a Zoom room and everyone comes in and goes. My only feeling is that no one might show up. But you can create a room where there is everyone coming in and they can talk to each other. And it's also possible that if suddenly 2 people want to talk something on their own, you can create another room immediately and have just 2 of you in a big room of 30 people.
That's true.
So
we can also attend
it's
each other's.
possible, but the etiquettes, how do you handle it? All that might be the confusing part.
Well, we build actual physical rooms like in the same way. In the physics department, we have a room that's dedicated, that's empty most of the time, but sometimes there's students in there.
Yeah, but I see people using it. I think Moses uses that, and I see few people using it.
Yeah. That's what I mean is that I think it would be used. There would be times it would be empty, but I think the virtual classroom would be, and just
so I can create such a room for you guys, or would you like me, or would you guys like me to take an initiative for that? Create a Zoom room for the whole physics department, and anyone can show up there anytime.
So I mean, I wouldn't be opposed to it because it would be nice to just have a place where, you know, I can say like, hey, Moses, you're working on homework 7 or homework 6. And
Like-
instead of saying, okay, well, how are we going to communicate to each other? Just via text message or group me? Instead of doing that, we can be like, hey, you know, just have a live feed where we can communicate to each other.
Yeah, so we'll call it the physics lounge or something. That's
Yeah, that's nice.
on Zoom, right? Physics lounge on the Zoom kind of.
Yeah, I
Right,
think
on-
that would
That's
be.
good.
I think that would be good.
Yeah, let me bring this up. What I can do is because our university has a license for these purposes. Like we can do a lot of things on Zoom as far as it is useful. So I can write this to our chair and Bob. I think Bob should be able to open this immediately. I can also open it. My only challenge would be that I can have only one room running at a time.
Mm.
So whenever I have a classroom, I'll have to shut it down. Otherwise, I can keep a room open forever, kind of. So let me see. Yeah, let me see how it goes. Like I'll do that today itself.
Yeah, just
And
make sure
copy you
there's
guys.
just make sure there's virtual coffee.
Yeah, right.
Virtual coffee, yeah. And which will be charged also. If I send this to the department.
Nobody's gonna show up.
Oh,
No,
okay.
this might be good. And just for chatting, like these kind of chats also are important, I feel. Yeah,
Mhm.
yeah, okay. Maybe, okay, good point. Yeah, and you guys don't mind me addressing to the whole department in
That'd be
a
great.
sense, right?
No, I think that would be fine. Yeah.
I think every time Scott keeps sending us messages, he keeps telling us, do you guys need to talk other than the subject, like other than the lab? If you need anybody to talk to other than your cat, we can just have a discussion like that. So yeah,
Yeah.
Scott is trying to get
Yeah, I
to.
think everyone wants to, but then, yeah, there's, this is a good thought. I mean, maybe a launch might help. And like all of us, like sometimes when we are working in the department, okay, let's take a break. Let's go and in the excuse of getting a coffee, let's go to the launch kind of.
Yeah.
Something like that. Yeah, maybe. Okay, good. Let's see.
Okay.
Okay. Yeah, let me initiate that. At least the last 3 weeks, no, 2.5 weeks remaining. But, still, it might be okay. Yeah. Okay, good.
Okay. Well, thank you.
Yeah, thanks. That's
Thank
awesome.
you.
Okay.
Appreciate your help.
Yeah. Enjoy this. Yeah. Take care. Yeah.
Bye.
Yeah, have a good afternoon, guys.
You too.
Yeah.
See ya.
Good afternoon.